Hi everyone, this lesson is going to be about the travelling salesperson problem. So this is a classic mathematical problem. Imagine there was a travelling salesperson who wished to visit a number of different towns. Now they would only want to go to each town once, and they would want to plan a route where they could start from home, say visit each of the towns in some sort of a sequence and return back home without having to waste time by backtracking to the same town. This problem was studied first by a mathematician named Hamilton, and so these sorts of paths and cycles are called Hamiltonian paths or Hamiltonian cycles. And if we recall our previous lesson with our definitions of paths and trails and so forth, pretty much Hamiltonians, we're looking at this last row. The distinction between a path, remember, and a cycle is whether it was open or closed. If it is closed, then the start equals the finish. We call that thing a cycle. If it was open, so the start and the end were at different vertices, we call that a path. But most importantly, no repetition of vertices. Now, unlike the Eulerian trails and the Eulerian circuits we did last time, we don't have to use every single edge. The most important feature of the travelling salesperson problem is that we do not visit the same town more than once. No repetition of vertices. And of course, to be a path or a cycle, we still need to have this condition true, that we have no repetition of edges. So, let's take a look at a couple of examples of these things. Here's our first one. Name a Hamiltonian path for the graph shown here. So to be very clear, let's be very clear. It says Hamiltonian and it says path. So that means we don't repeat edges, we don't repeat vertices, and a path is open. The start does not equal the finish. Now there is no simple way to find these. You just have to do both trial and error. So let's try by starting at vertex A. We could run across here to B, then perhaps down to D, over to C, down to E, over to F, and then finish at G. Have we visited each vertex just the once? Yes. Did we use all edges? No, but that doesn't matter for Hamiltonians. So we would state our answer just by naming the vertices. We went A, then we went B, then we went D, then we went C. This is not the only possible answer, I should say. Then we went E, then F, then we finished at G. Be careful that you don't put that final edge there. If you did go back to A, you would not be answering the question because it would no longer be a path, it would be a cycle. Now should stress there are many other answers that are possible for this one, and of course there's no fixed method, not like the Eulerians where we counted the degrees of the vertices. For this one it is trial and error. Let's try another one. We've been asked to find a Hamiltonian cycle. Hamiltonian, so no repetition on edges or vertices are allowed, and cycle means we want to start and finish at the same place. Let's begin here at P. Could go Q, then we could go down to R, then S, then directly to T, and then back to P. So we have a cycle because we start and finish at the same place. So I could start from P, let's just go Q, then where did we go? R, we went across to S, then we went to T. Now don't forget to put P at the end of this one because we did finish by going back to where we started. Once again, not the only answer, plenty of other possible answers. Make sure you start and finish at the same one, and make sure there are no other repeat vertices. So remember the first and the last, they're identical to make it a cycle. There, that makes it a cycle. Everything else in the middle must not appear any more times. Last example. We want a Hamiltonian cycle. Okay, so we just did one of those. But this time there's an extra stipulation. It must begin at C. Begin at C does not include this edge. So let's just put a little circle around where we want to start and That's where we want to finish. And we're not including edge, so there's some problem with that edge there. We cannot use that edge. Okay, let's try. Trial and error time. Let's go C to D. Now if I went across to E, then I went down there, I'd be stuck. So I might go to F and then back up to E, and then I think I could find my way around the rest of the network and back to where I started from. So what did we do? C, then we went D, then F, then we went back to E, H, G, I, then we went A, B, and finally finished at C. Okay, that's it. Hamiltonians. Hamiltonians, if we were to go back to our little table, which describes all these different sorts of things with networks, the Hamiltonians are the bottom row of the table. Typically, we talk about Hamiltonian paths or Hamiltonian cycles. Remember last time when we were doing the Eulerians were the second last row, the middle row, weren't they? These ones. These were the Eulerians, which we did last time. And of course, with the Eulerians, typically we wanted to know about trails or we wanted to know about circuits. The big thing with the Eulerians was that every edge must be included. With the Hamiltonians, we don't mind if the edges are not all included, as long as every vertex is included. Hamilton was more concerned about the vertices being covered, and Euler was more concerned about the edges. Okay, so just be very clear, and I hope that little table there helps to organise your thinking and organise these ideas for you. That's it for now. Thanks for watching.